Welcome to the Surfon Infrared Learning Series. This episode, Ep12, Michelson Interferometer, the heart of fur, then close with the checklist. Next, prologue, a failed experiment that changed physics. In 1887, American physicist Albert A. Michelson and chemist Edward Morley conducted an experiment in Cleveland to detect Earth's motion relative to the luminiferous ether. The result was astonishing. They measured nothing. This failed experiment disproved the existence of the ether, paving the way for Einstein's 1905 special theory of relativity. Michelson was awarded the 1907 Nobel Prize in Physics, becoming the first American to win a Nobel Prize in Science. Next, structure of the Michelson interferometer. The Michelson interferometer in third consists of four key components. LPH. Table 1. Core components of the Michelson interferometer. Data. Sources. Librichix, Newport and next, principle of interferogram generation. 2.1 Constructive and destructive interference. The essence of interference is the superposition of two light. Next, I transform from interferogram to spectrum. 3.1 Mathematical relationship. The interferogram I delta Rab and the spectrum B sigma Garfin form a Fourier transform here. Next, resolution and moving mirror travel. The spectral resolution of fur is determined by the maximum travel of the moving mirror xe. Del tilde nu equals fracone 2L$. Next, beam splitter materials. Beam splitter materials must be selected according to the spectral range to ensure good transmittance and appropriate refractive index in that range. 5.1 Beam splitters for different spectral regions. Next, Nyquist sampling theorem. Nyquist-Shannon sampling theorem. To faithfully reconstruct a continuous signal from its discrete samples, the sampling frequency Fs must be at least twice the highest frequency max present in the signal A. $Fs eg chusu jolt F max $. Next, abordization. 8.1 Why is abordization needed? The moving mirror travel is finite. The interferogram is truncated at plus or minus L. Mass B. This is equivalent to multiplying the interferogram by a rectangular function, boxcar. Next, X phase correction. 9.1 Why is phase correction necessary? An ideal interferogram is symmetric about ZPD, and a cosine transform yields the correct spectrum. However, actual interferograms have phase errors phi semi-abium due to the following reasons: collision. Next, X. Zero filling. 10.1 What is zero filling? Zero filling is the addition of zeros at the end of the interferogram to increase the number of data points before performing the FFT. Next, goal evolution of interferometer design. 11.1 Classical Michelson interferometer. The classical design uses a plane fixed mirror and a plane moving mirror. The structure is simple, but it is extremely sensitive to tilting of the moving mirror. Any angular error alpha causes the returning beam to deviate by 2 alpha. Next, Michelson's historical legacy. 12.1 Michelson-Morley experiment. Albert A. Michelson, 1852-1931. Next, review questions. Why does the interferogram have a sharp center burst at ZPD? What will the detector see if the moving mirror stops at ZPD? To achieve a resolution of 0.5 centimeters, how far must the moving mirror travel? What about 0.01 centimeters? Finally, the drill actualists. Make sure you can recall each item. Interferometer structure. Beam splitter plus fixed mirror plus moving mirror plus detector. Interferogram generation. Optical path. Difference of two beams varies with moving mirror. Movement, producing interference. Center burst. All wavelengths add in phase at CPD, forming the maximum peak of interferogram. Fourier transform. Mathematical transform from interferogram, spatial domain to spectrum, weighted number domain. Resolution formula. 1. 2L, where L is moving mirror travel. Beam splitter materials. MMMLK bros, hygroscopic, near-rear mylar C, N8 laser, 632.8 nanometers. Each fringe corresponds to 316.4 nanometers moving mirror. Travel used for sampling trigger and wave number calibration. Nyquist theory. Sampling frequency greater than or equal to 2 times maximum frequency. Hin sampling corresponds to 15,800 centimeters Nyquist frequency. Apodization function. Truncating interferogram causes sensei lobes. Apodization suppresses them but reduces resolution. Phase correction. Mertz method is preferred for commercial instruments. Corrects electronic optical phase errors. Zero fading. Increases data point density, but does not increase optical resolution. Polar cube retroreflector. Standard in modern fur. Tilt resistant. Replaces plane, moving mirror. Michelson history. 1887 Morley experiment. 1907 Nobel LIGO gravitational waves. Part of modern fur. That covers the required sample for this episode. Practice with real spectra on cell phone, and continue with the next lesson.